Okay, so thank you very much for having me here. It's a great pleasure to visit again. I think last time I was here was exactly 10 years ago, during the monsoon workshop in 2008. I was very young, and as Abhijit said, without any gray hair. But, okay, so I will be talking about, in this series of talks, I will be talking about the general program of understanding 4D supersymmetric field theories by engineering them starting in 6 dimensions. So there is a big program that I will review. But in this first talk, this seminar talk, I want to talk about a very, very simple example of this program. And this is based on a paper we wrote recently with Gabi Tzafrir, who is at the moment a postdoc at IPMU, and he's really exceptional. And instead of starting with a general motivation about this whole program of starting from 6D and going to 4D, which I promised to review in great detail in the later talks, I start with a very, very simple physical problem, which we'll try to understand. So consider n equal 1 supersymmetric theory in 4 dimensions, which has SU3 gauge group and 9 flavors. Okay? It's a very, very simple model. SU3 is special, as we all know. It's what we see in nature, but it's also special in the following respect. Naively, this is an IR-free theory. So if you take a generic NF equals 3n theory, a theory where the number of flavors is thrice the number of colors, this is an IR-free theory. This is at the edge of what is called conformal window. However,
fundamentals, of course, right?
These are all fundamentals. So it's 3n fundamentals and 3n anti-fundamentals. So this is all true except for the case of SU3. So for general n, this is the case, but for the case of SU3, this doesn't work. And this is not an IR-free theory. It's a theory which has actually a very large conformal manifold, a 7-dimensional conformal manifold, which passes through zero coupling. Okay? So, and the way the reason why SU3 is different is because we have a large number of marginal operators that we can build. Basically, baryons and antibaryons are marginal. Okay, so there are a lot of marginal operators, and some of them turn out to be exactly marginal. So if you do the counting, there are many marginal operators on a general point of the conformal manifold. All the symmetry is broken. So the number of all the possible marginal operators you can write for this theory minus the dimension of the symmetry group turns out to be 7. So this theory has a 7-dimensional conformal manifold. And again, this will be important in what follows. All the symmetries of this theory are broken on a generic point of this conformal manifold.
So just let me remember, so at one loop, the gauge coupling doesn't run?
No, the one loop gauge coupling is 0.
And at 2 loops?
And the 2 loops it runs and it becomes IR-free theory. Okay? But here, if you just turn on the gauge coupling, it's still true. Okay? But what happens is that you can turn on these other couplings, these other marginal couplings, and you have this huge number of marginal operators, so you can find a subspace, a 7-dimensional subspace, such that the beta function will be exactly 0 to all loop.
You turn on the gauge coupling and something.
Exactly, yes. So you need to turn on something, you know, what exactly you turn on, you need to compute. It's something you need to work order by order, but you can show by some generic methods that there exists a 7-dimensional submanifold on which the beta function is 0, which is a conformal manifold of this theory. Okay, so sorry.
The superconformal representation of the marginal operators and the global symmetry.
Exactly. Yes. So there is type of a Higgs mechanism that a marginal operator. So what the content of this paper, Green, Komargotsky, Seiberg, Tachikawa, and Wert, is that a marginal operator can cease being can be two things: either exactly marginal, or it can be marginally irrelevant. And the way for it to become marginally irrelevant is to meet a conserved current and to form a long multiplet, and then just become marginally irrelevant, not to be exactly marginal. Okay.
And the R symmetry which governs the dimensions, etc., the conformal.
It's a free R symmetry. It's important. So this is a conformal manifold. There is a free point, and then there is a conformal manifold which is 7-dimensional, which passes through this point. So anything you can deduce from the free point is still true. So the R symmetries of the fields are 2/3, are the 3 R symmetries.
All along the.
All along. This doesn't change along the flow. Okay? So we will come back to this in a slide. So this is a very special case. SU3 is a special case. And here I will steal some slides from Strings conference, which happened this summer. So we are celebrating 50 years of string theory. So John Schwartz gave a very nice talk, as also Shiraz did, but I didn't steal Shiraz's slides. I stole John Schwartz's slide. So he gave lessons that we learned from string theory. So one lesson is to take coincidences seriously. So this is not some kind of huge coincidence, not like these ones, but it's still a coincidence that we should maybe understand better.
What is the coincidence?
So that SU3 is special. SU3 has a special conformal manifold which passes through zero coupling. Okay?
That also is not trivial, the phi that passes through zero coupling, right?
Well,
It could have been the case that it may not pass through this, right?
we know of many examples where we have conformal manifolds which do not pass through zero coupling. The cases where we do pass through zero coupling are very rare. They are very rare if we have a single gauge group. With many gauge groups, say SU2 to the n, or SU2, like if you have many factors of simple gauge groups, it is easy to engineer cases with conformal manifolds passing through zero coupling. With one gauge group, it's rare. There are several examples that you know of. One is n equals 4. So n equals 4 is such a case. And there are a few examples with n equal 2. Supersymmetry. But with n equal 1 supersymmetry, this is the only example I know of.
Actually,
Okay.
what are the examples where the conformal manifold does not pass through zero coupling?
Well, for example, SU2 with 4 flavors has a conformal manifold, but it doesn't, it's a strongly coupled conformal manifold. You don't pass through zero coupling. Yes. Okay, so this fact was, stressed to me by Zorko Margotsky several years ago, like 2 or 3 years ago. So again, the nice feature of this theory is that it passes, it has conformal manifold which passes through zero coupling, and the conformal manifold is large. So in the cases that I mentioned with n equals 4 supersymmetry and with n equal 2 supersymmetry, when such things happen, we usually know of some duality group, some interesting duality groups which acts on the conformal manifold. So weak strong coupling types of duality that we have a weakly coupled theory, and then we have an equivalent description, some kind of a description at strong coupling, which is given in terms of a dual weakly coupled gauge theory. So the question which Zor asked me, is there a dual description like that here? Is there a duality group acting on such a conformal manifold? So this is question number 1. Question number 2 is that there is a kind of a numerological magic here. So we have 9 flavors. Okay, 9 flavors, 9 fundamental flavors of SU3, so which is 3 times 3 times 3. So we can think of this theory that we are considering as combining 2 trifundamentals of SU3. So this 3, 3, 3 denotes a trifundamental of SU3 if you want more usual quiver notation. So this is the basic building block. We have 3 bifundamentals of SU3, and we combine 2 such things together. Okay, this is a quiver way of writing this theory. Now, trifundamentals played an important role in recent years in understanding geometrically gauge theories, what is called class S theories. For example, if you take trifundamentals of SU2 and build theories from these trifundamentals, you can, the claim is that the theories you obtain can be obtained starting from 6 dimensions and compactifying certain 6-dimensional theory and an A1 2,0 6-dimensional theory on some general Riemann surface. And the genus of this Riemann surface and the number of punctures just are obtained topologically from this gluing. So for example, if you have a one trifundamental and you glue to it a second trifundamental, you would obtain a genus 1, a theory which you obtain from compactifying from 6 dimensions on genus 1 surface with 2 punctures, and so on. So there is a geometric picture which comes with these theories. Yes?
Your rough point will be, is it that you will get a 6-dimensional theory which you will compactify and get this spatial?
Yes, that we will.
And this spatial facts of SU3 will sort of come from 6-dimensional.
That's right. That's right. That's what we will eventually do. We will understand. So there are two questions. One is whether there is a duality group acting on this conformal manifold, which is hard to understand in n=1 language. And another question is there a geometric picture? Again, in a sense, is there a 6D theory, which you can compactify on a Riemann surface, and the theories you will obtain will be of this kind and generalizations of that, taking trifundamentals and gauging SU3 symmetries and building generic Riemann surfaces. And these two questions are related.
You
Yes.
say you put two of these together, that's the Q and the Q bar?
Yes, exactly. So this is, yes, so this block says Q, then we have another block which is Q bar, and we gauge a diagonal combination of SU3. Okay, and that's exactly the model we have. And now what you can do, you can write this block as trifundamental of 3 SU3s, this is just a picture. And now you can start combining these blocks in arbitrary way by gauging all the possible SU3s and obtain theories which you would naively correspond to a Riemann surface. And the question is it so? Is there a theory in 6 dimensions which gives such a picture? Yes?
Did you say that the global symmetry is broken?
Exactly.
in the form manifold?
Yes, it will be very important.
Yeah.
Yes.
So in general, you cannot, as it is, combine them, right? Because
You can.
So the picture suggests that there is global symmetry, but it's
No. Okay, so we will review it in a moment. There are two types of global symmetries. One global symmetry is corresponding to the puncture, okay? And then there might be other global symmetries, okay? For example, this theory has a baryonic symmetry somewhere on its conformal manifold. It's not broken, but on a generic point, it will be broken, okay? So these types of baryonic symmetries will be broken. And actually, in this case, we will review it. Also, the symmetries which correspond to these SU3 symmetries will be also broken. This is a bit jumping ahead. You know, there are subloci of the conformal manifold where you keep these SU3 symmetries. Okay.
I thought this representation theory would tell you that the favor symmetry.
Just wait. It's a very good question, but I need to tell you more to discuss it. It's a very good question, and actually it turns out to be a very non-trivial question, and it is related to your previous question of conformal manifolds not passing through origin. But that will come in the middle of the talk. So if I don't answer your question, let me know. Okay, so when Zor told me these facts, I thought, okay, these questions, I thought, okay, these are very interesting questions, but I don't have a machine which turns cute observation into physical, physical observations. And 2 years have passed, 2 or 3 years have passed, and we learned a lot about these relations between 6 dimensions and 4 dimensions. And several months ago, I remember these questions and understood that actually now the answer is almost immediate, okay, to both these questions. We do have a machine which turns such question, can generate answers for such questions. And that's what we will do today. We will answer this question, and it will be an example of how this program of relating 6D and 4D theories works. And can generate interesting physical facts. So this is lesson number 3 from John Schwartz, and that's how the answer goes. So when working on hard problems, you should generalize, and that's how we will answer such a question. We will think of it in a bigger framework of these compactification scenarios. Again, I don't compare the importance of the questions, but the lesson is a very generic lesson. Okay, so this is what I just said. We have learned a lot in recent years, and we have a rather straightforward algorithm. So starting from a 6D theory, we take it on a Riemann surface, and we produce 4D theories. So that's the procedure. And this algorithm is very straightforward. Okay, we can generate a lot of predictions about 4D theories by following this algorithm. And what we will do today, we will reverse engineer this algorithm. We have some nice theories in 4 dimensions. They have some nice properties. So we'll ask ourselves, how can we fit these theories or these observations in this picture? The reverse engineering in general is not unique. It's in general hard to do. But in this case, exactly because it has so little symmetry, this will be the important thing here. These theories have very little symmetry, and that will actually allow us to fix to reverse engineer this algorithm. In general, when you have a lot of symmetry, there are a lot of knobs and levers that you can play with, and reverse engineering is hard. and you cannot do it, but here we can. So this is what we will do today. So before jumping into describing the algorithm and trying to reverse engineer it, let me give you a one-slide summary of what was done in recent years in this program of going from 6D to 4D. Again, if you will come to the other talks that I will give, I will review this well, some aspects of this in a lot of detail, but just to have a general picture here.
Large bits. The mapping class group of this two-dimensional.
Yes.
Sort of non-trivial.
That's right. It in general becomes the duality group of the gauge theory in 4 dimensions. Okay. So that's exactly how we will answer this question about the duality. We will understand how to embed this theory in this type of framework, understand to which surface it corresponds, and then that will tell us what type of duality groups acts on this conformal manifold. Okay. Yes.
Get to that. But by free theory, the flow passing to free theory, you mean free gauge coupling or?
Free gauge coupling, like everything free. It's like zero coupling. Yes, everything free. Yes, everything zero. Okay, so in recent years, we have learned a lot from this engineering on 4-dimensional theories from 6 dimensions, and it all started with this seminal paper by Davide Gaiotto, also I think exactly 10 years ago. Okay, and what he did, he started from what is called 2,0 theory, the theory living on M5 branes, compactified them on Riemann surfaces, and got a lot of theories in 4 dimensions. And a lot of known facts about 4 dimensional n=2 theories could be explained in this way, and a lot of new knowledge was generated. So this was a very influential paper. And later on, there were several generalizations of this picture to n=1, to cases with less supersymmetry. So one thing one can do is, instead of starting with 2,0 and making choices during compactification such that n=2 supersymmetry is preserved, one can start with the same 2,0 theory in 6 dimensions, but make more generic choices which would preserve less supersymmetry in 4 dimensions. And that is called n=1 class S, and this was done originally in the paper of Benini, Tachikawa, and Wecht, straight after Gaiotto's paper appeared. And then there was a generalization by Bim, Bobev, and Wecht, BW, who classified the most generic choices. So in this way, one can generate a lot of n=1 theories, but in some way, they're all related to n=2. The starting point is in the same in 6 dimensions, so you can generate a lot of interesting things, but they are very related to n=2 dynamics. Now, the point is that in 6 dimensions, there are many more superconformal field theories than just 2,0. There is a large class of 1,0 theories, and I saw on the website that Laszkia Bardwaj gave a series of talks discussing these theories last year. So you heard about them. So there are many choices you can make in 6 dimensions. And then you can take any of these choices and compactify them down to 4 dimensions. So several cases were analyzed, the cases of so-called ADE conformal matter, and we will discuss them in other talks. And you can go through with this compactification procedure and produce a lot of theories in 4 dimensions. Now, in general, you can predict existence of certain field theories. You can compute some properties of these theories, as we will review, symmetries and anomalies, but you don't have a useful Lagrangian description of these theories, not at the moment. You don't have a Lagrangian that will produce these properties generically. So some of the cases you can. Exactly these trifundamentals of SU2 that I mentioned, these are taking A1 2,0 theory, the 2,0 theory which lives on 2M5 branes in 6 dimensions. And if you compactify it, you get Lagrangians which pass through 3 points, and you can get Lagrangians. n=4 you can generate in this way. n=4 is compactification on a torus for any group. So it is also a Lagrangian. But if you, for example, a way to engineer it is to take the AN-1 type 2,0 theory, the theory living on n MF5 branes on a torus. Then you get a theory with a known Lagrangian. But if you take compactification on a generic Riemann surface, you don't know what a Lagrangian is. Okay, so there are certain classes, and there are classes of models which are written here. So the way the classification goes here is the second group is the type of 2,0 you take, and the first group is the type of singularity you put this 2,0 on. So if you take A1 type of theory and no singularity, you can write any Lagrangian you want. If you take actually A2 type of membranes with no singularity, you can also find some types of Lagrangians. A1 types of membranes on Z2 singularity, we can also understand the 4D theories with Lagrangian constructions. And this is called E-string, just one M5 brane probing D4 singularity. This is called an E-string, and there we also can understand Lagrangian, and this I will discuss in detail in one of the following lectures. So for some cases we know Lagrangians, for generic cases we don't know Lagrangians. For special compactifications, as you refer to, for example, the torus and some other cases, we also know Lagrangian. So for some more generic choices of 6D theories, but some special choices of geometry. Okay. But with these more general choices of 6D theory and general choices of geometry, we don't know what the Lagrangians in 4D are. So this is the situation today. So there is this program of trying to understand the 4D theories. This is a program I'm involved in heavily, and there are other types of approaches. For example, one approach is not to care about what is the Lagrangian of 4D theory, just to build a large class, predict a large class of 4D theories and study properties of them and what happens if you combine them, if you gauge some diagonal symmetries, and what type of properties this more abstract set of theories in 4 dimensions satisfies. And this is mainly pushed by Jonathan Heckman and many collaborators.
When you say compactify on a manifold without singularities, you include punctures.
Yes. So, well, there are two types. There are these which type of singularities? I mean, this singularity? Yeah, these are two different singularities. So you can have some orbifold singularity, and then you put your M5 branes on it. So this is one type of singularity which appears there. This changes the theory you have in 6 dimensions.
Right.
And then there is another type of things that you can have, and these are punctures on Riemann surfaces. So Riemann surface can have holes in it, and you will need to define what the boundary conditions of the holes are, and so on.
So for instance, when you say A0, A1, you include all these.
So this is not this. I'm talking just about the 6D theory. So I'm talking about this singularity. What is this singularity? Okay, so this is the general story. So how does the algorithm work? So now I will review what are the basic things that we can deduce about 4 dimensions starting from 6 dimensions. So there are very, very robust things that we can predict. For example, we have a choice. We have several choices to perform this compactification. One choice is the choice of the 6D theory, which I denote here by T. Another is a choice of this surface, which I denote by C. And also the 6D theory can have some global symmetry, which is in general important. And when you compactify, you can turn on classical configurations for this gauge symmetry, some fluxes or holonomies around cycles. Okay? So for these different choices, in general, you will get a different theory in 4 dimensions. So fluxes are quantized. So this is some discrete set of choices. So you will get a discrete set of theories that you can generate in 4 dimensions. So, which are classified by choice of 6D theory and choice of flux.
So you are not including R symmetry?
No. Yes.
Sorry to be so remedial, but the flux here corresponds to a flux on the M5?
On the Riemann surface. So we have a 6D theory, wherever it comes from, M5 branes, F theory construction, whatever you want, you have some 6D theory. And then you can put it has some global symmetry. And when you put it on a Riemann surface, you can choose to turn on some flux, some background flux for this global symmetry. This flux will break explicitly some of the global symmetry. Okay? You turn on explicit configuration, so you break some of the global symmetry. So in particular, what you can... Yes?
It's a magnetic flux threading your two torus.
That's right. This is integral of F on your torus. Okay.
Thank you.
So we can turn on this flux and it breaks the 6-dimensional symmetry. So in particular, we can predict what the 4-dimensional symmetry is. We expect the 4-dimensional theory to be determined by the symmetry in 6 dimensions, which commutes with your choice of flux. Okay? There is some subgroup of the 6D symmetry which is preserved by the choice of flux, and that we expect to be the symmetry of 4D. Okay, so again, starting from a single theory in 6D, we can generate many different theories with many different global symmetries depending on the flux. Now, in many cases, we also know the anomaly polynomial of the 6D theory. Okay? By various techniques, the anomaly polynomial of the 6D theories can be computed, although these theories are strongly coupled and complicated. People have computed anomaly polynomial, so we can just take that anomaly polynomial and integrate it over the Riemann surface on which we compactify in presence of these fluxes. And this will produce a 4-dimensional anomaly polynomial. So we can predict not just the symmetries of the 4D theory, but also the anomalies. Okay? So these are very two robust predictions that we can have, which don't depend on the details. Like, we don't know much about these 6D theories, but we can predict these things. Okay? We can predict other things. For example, in general, we can predict the number of marginal and the relevant operators that these theories will have. For example, some of the marginal operators correspond to the complex structure moduli. So the surface on which we compactify has some parameters entering in the complex structure moduli. The number of them is 3g minus 3 plus s, where s is the number of punctures and g is the genus. So we would expect the number of parameters of the 4D theory, and parameters in 4 dimensions are couplings, like that's what we can call parameters. And we would expect to have at least so many of them. And then we can have, if we have global symmetry, we can have also holonomies. Holonomies are continuous parameters, and holonomies also parameterize part of the conformal manifold. So we can write expressions, formulae to how many marginal operators we have, and also how many relevant operators we have.
Roughly, what is the technique for the relevant operators?
So I will discuss it in the lectures. It will not be important here because we don't have symmetries. The theories that we will have here will not have relevant operators. That's why you don't write them. But roughly speaking, you basically, okay, so the way it goes, you start in 6 dimensions, and what you know about the 6-dimensional theory in general, that it has a stress energy tensor, and it has a conserved current for this global symmetry. So you take those operators and look what becomes with them when you go to 4 dimensions. You basically use Riemann rock to understand what are the charges and what are the properties of the operators which reduce from them. What will come from stress energy tensor are these operators. And from conserved currents, some of them will be marginal and some of them will be relevant, depending on the charges. So you just apply Riemann rock to those operators, and I will discuss it, I think, in the lab.
It's clear that these are the only.
No. Excellent point. This is a generic prediction, and it almost always works, but it fails. For example, one thing which can happen, this is kind of a naive prediction. Okay? This is a naive prediction that for generic compactification actually works, but for special compactification it might not work. For example, on tori, when you compactify on tori, this often doesn't work. And there are kind of many hand-wavy explanations. We don't understand it fully. For example, one thing that can happen that you can have other operators in 6D, which will give rise to relevant and marginal operators in 4D. You can have non-local operators in 6D. So here we reduce local operators, but there can be like surface operators wrapping the surface, which will give rise to local operators in 4D, and they can give rise to relevant operators and marginal operators. But if you get like a large surface with a lot of handles, complicated surface, you would expect all this other stuff to have large dimensions. So generically, these will be the only ones. But that's true. Like for low genus and special compactifications, there can be other things happening.
Again, sorry for this remedial question.
Yeah.
The two toruses, the two-dimensional surface is in general non-trivially fiber or 4D based to give the 6D?
No. Generally, we will take a trivial. Like it will be a direct product of the 4D theory times the torus. Well, it's an interesting question if you fiber, but well, it actually becomes important when you go, it plays a role, but not in what I'm going to talk about. And well, yes, we can. Well, this type. Well, okay. I don't have something very simple to say, but I'm not going. The things I will going to discuss have a trivial vibration, so it's a direct problem. Sorry. Yes, there are works, and it also relates to 3D compactifications. And
By the way, this integration of the 60 anomalic polynomial on the two surface to give you the 4D anomalic polynomial. If this surface has punctures also, then also it's known how to compute.
yes, I will review it in a moment. So, okay, yes, you are asking excellent questions, but I will review it in a moment. So maybe to say something about this, this is, for example, something which appears in some sense in all this started from the papers of Gaiotto and Witten, and so we'll say on the duality walls in n equals 4. So you can have an n equals 4, then a domain wall, and then on the other side you have a duality. So in this language you can think of the 4-dimensional theory as in some sense fibered, like it's a torus, but you change the coupling, and so there are. So there are such things, but they are more complicated than what I want to discuss. Okay, so now let me go to punctures. Okay, Abhijit's question and Shiraz's question from before. So,
Sorry, one
yes.
other stupid question. I mean, you talked about turning on these global symmetry fluxes.
Yes.
And turning that on generically breaks some supersymmetry?
Yes. So generically the statement is that you can always do that, preserving n equal 1 supersymmetry in 4D. But if you start from, say, 2,0, which has more supersymmetry, or, say, 1,0 theory sonnet torus, which also has 8 supercharges, then if you turn on generic such fluxes, you will break to n equal 1. You will break half. But it's always possible to preserve 4 supercharges in 4 dimensions. That's the statement. Okay, so now we want to discuss what happens on the punctured Riemann surfaces. And here it is very important, a very important ingredient is to go through intermediate 5-dimensional picture. So what you can do is start from 6 dimensions and then put your 6-dimensional theory on a circle. Okay? And the idea here is that when you want to compactify on a space with a puncture, you can think of a puncture as a long tube, as a long cylinder, a long thin cylinder. Okay? And then the theory effectively, which sits on this cylinder, is described by 5D theory, 5D effective theory. Now, in some cases, not in all cases, but in some cases, this 5D theory that you get on a small circle is a gauge theory. Okay? It's a 5-dimensional gauge theory, and we know what it is. Again, example is you take 2,0 on a circle. Well, the claim is that you get maximally supersymmetric Yang-Mills in 5 dimensions. This theory doesn't have a UV completion in 5 dimensions. The claim is that the 6D theory is the UV completion. But this is the effective theory on the long cylinder. There are more cases where you get a gauge theory description on a cylinder. And the claim is that when you have such a gauge theory description, you can understand what punctures are. So you start with an infinite cylinder, just compactify on a circle, but then you make a puncture. You cut the cylinder at some point. You have a boundary, and then you need to specify boundary conditions at that boundary. So there are many choices of boundary conditions which preserve the supersymmetry you want. One of them is called maximal choice, and that's just giving Dirichlet boundary conditions to the vector fields, so vector gauge fields of the 5D description. Okay, so you're basically freezing the 5D description, gauge theory description, and you do something to other fields that you have, and that depends on the particular theory that you have. And what happens is that punctures will have some symmetry coming with them. The gauge symmetry of the 5-dimensional theory becomes flavor symmetry, becomes global symmetry. So each puncture comes with some global symmetry, which comes from the gauge theory description. You can choose other boundary conditions such that you will preserve subgroup of the gauge, like that the flavor symmetry will be subgroup of gauge symmetry, but we will only discuss these maximal choices. Okay? And when you glue punctures together, when you geometrically kind of undo this procedure of cutting the cylinder and inserting a boundary condition, so there are Dirichlet boundary conditions here, you just gauge the symmetry. You make this dynamical. You gauge the symmetry which you have frozen. So there is this geometric way of understanding how you combine two surfaces together along the puncture by gauging this 5D
Let me ask
symmetry.
an extremely stupid question. If you, when you compactify on some surface, there's a volume of that,
Yes.
and that introduces some effective mass scale in 4 dimensions.
Right. So the statement is that we go, all the statements I'm making is to go to energy scales far below that scale, the scale. So we'll first compactify on something which has finite dimension, and then we go consider an effective theory which is low energy effective description, and then we're asking the question: is there a 4D description which flows to that effective theory?
Right. But what I was wondering was, you seem to generically get conformal dynamics.
No. Well, very often it's true, but there are cases where you have non-conformality, like you have IR-free theories, or like either just free fields or IR-free gauge fields. There is no generic statement that in general you will get a conformal, interacting conformal CFT. When you do these things, it's true that usually you get conformal theory, but it's an experimental result. I don't have an argument for that. And there are counterexamples. Okay, there are, for example, if you take most of the theories, 6D theories that you will take and put them on a torus, will actually give rise to IR-free theories on a torus without flux. Okay, n equals 4 is actually 2,0 on a torus is a special case. It's not IR-free, but generically you will get an IR-free theory. On more general surfaces, actually, I don't know of an example where you will get an IR-free dynamics, which if you have a general genus G surface, I don't have an argument why it has to be so.
And just in Gayotto's case, why did he always get conformal dynamics?
I don't know.
On the sphere, not right?
Well, on a sphere, okay, sphere is special, yes. But sphere, yes. Sphere we don't really well, and so actually, okay. On a sphere with no flux, in general, it is we don't even know what it is, let me put it. It's probably, maybe there is a mass gap, maybe there is some IR-free dynamics, I don't know. But if you put flux on a sphere, so sphere with flux actually gives good theories. Okay, sphere with flux in general will give theories which, some theories are just free fields, free chiral fields, and some theories will be interacting as CFTs.
But if you want to preserve n equals to 2, then there is unique choice of flux.
Yes, but then I don't know what the theory will be. I think it will be some either, it might be some IR-free theory. I don't know what it is. Okay.
I'll just keep asking that.
Yes, sure. Great.
You talked about how this puncture was like a tube.
Yes.
So what you're doing is a wild transformation in this 2 dimensions to make that puncture a tube, right?
That's right. So, right. So the statement is that the theory you would get in 4 dimensions is independent of this stretching.
Because the original theory was wild. Because the original 6 dimensions.
Well, you might do something to the couplings of the 4D theory. You're going somewhere on the conformal manifold of the theory. So you're going on the conformal manifold to a description where you can describe the 4D theory to the point on the conformal manifold. You go to the point on the conformal manifold where the proper description of the theory is some weak gauging of 2 pieces. So you have 2 pieces corresponding to the left side and the right side of the picture, and you glue them together by gauging some symmetry. Okay? When you will make this cylinder short, you go to a strong coupling regime. But the claim is that it is the same theory in some corner of its conformal manifold. Okay. All these statements are non-trivial. I don't have like a proof of them. It's like many of the statements are just you do things and you find a consistent picture. And actually, some of the statements, I will not discuss them today, but discuss them in other lectures. We actually thought, why should they be true? But by doing computations, they turned out to be true. And
Is it not always the case that this moduli of the surface complex structure moduli?
no, not always. Okay, you're asking excellent questions. So, for example, you can compactify, as I already mentioned, if you compactify on a torus, so you would want to have at least one coupling, which is complex structure modulus, and that's what happens in n equals 4. But if you take other 6-dimensional theories, you might get theories in 4 dimensions which have no no exactly marginal deformations at all. So this is related to Shiraz's question. So the generic prediction is that you will get complex structure moduli, but it might be that complex structure moduli just is not a parameter. Once you are in 4D, it does nothing. Like there is no parameter which corresponds to it for some reason that we don't understand why. Okay, but it can happen. This is a naive expectation, and again, typically it is true, but we know of many cases, typically they are simple like torus or sphere, where these expectations fail. Okay.
So in that case, as far as the geometry of the torus is concerned, there's some special point.
Yes, exactly. I will a little bit discuss it more in the following lectures, but
this is true even if you preserve the
yes,
local,
yes.
Local translational symmetry without don't introduce.
Yes, it's not clear to me why this happens, but I think. Okay, so this is a picture of a summary of what I just told you. So we start from 6 dimensions. We make a choice of the 6D theory of the compactification surface of fluxes, and we produce 4-dimensional theories. We can predict symmetries, anomalies, deformations, and the symmetries take this form. There is a part of the symmetry which comes from the 6-dimensional symmetry which commutes with the fluxes, and then there is a part which comes from the punctures. So there are factors of 5D gauge symmetry as global symmetry, which are associated to the punctures. And again, this is the picture that I have drawn on the blackboard. So these are very robust generic prediction about 4-dimensional theories that we can have. And now the idea is to reverse engineer this algorithm. So not go this way, but go this way. We have an idea. What did I do?
And the reason the gauge symmetry became a global symmetry was because the tube was infinite?
No. We cut it. It's not because it is infinite. We cut it, and then we needed to specify some boundary conditions. So these boundary conditions that we chose were Dirichlet boundary conditions for the gauge fields. Okay, so we frozen them.
Oh, I see.
Okay, we can have other choices. For example, there are choices where there are we still have gauge symmetry. We don't freeze all of it. Some of it is dynamical, but there is actually a zoo of choices that you can perform. And all of these choices would give different theories in 4 dimensions. Not all of this is classified. This is kind of the most simple choice that you can perform. Okay, so now what we want to do is to reverse engineer this algorithm, starting from our simple theory. So the question is there a 6D starting point which will give us this SU3 SQCD-like theories? Yes?
Sorry, if you put a boundary condition that freezes the gauge transformations there, but it doesn't freeze it in the bulk of the tube.
That's right, but there is some like the point is that what you produce a flavor symmetry with which you can act on this gauge. There are frozen gauge fields at the boundary, and you can act with this group, with the gauge symmetry group there. So there is a flavor symmetry.
So that's the global part of the gauge symmetry?
Well, yes, I think you can think about it that way.
But in addition, there's also this local stuff.
Uh,
I mean, you're taking a gauge theory, you're putting boundary conditions at one end.
yes, you're right.
Keeps it a gauge symmetry.
Yes, you're right.
That doesn't have any implications. You're saying the gauge is
the statement I wanted to make is just that you're producing the flavor symmetry. What happens in the bulk? Well, I will care, but in the next talk.
And also, the final thing you are interested in is 4-dimensional theory.
That's right. And yes, that's why I don't care about it.
There is a thing that closes it up there, so it becomes a small
Right.
interval there.
So yes, what is important that there is a flavor symmetry.
dimension reduction.
We will discuss a little bit more what happens in 5D in the third lecture. Okay, so we want to reverse engineer this algorithm. So we start from this hint in 4 dimensions that we have this type of blocks, tri-fundamentals of SU3. We want to interpret these SU3 symmetries that we see as coming from punctures, okay? Because we are gluing things by gauging SU3. So that's what we would do if there is an SU3 symmetry coming from punctures, from reductions of 6-dimensional theory. So we'll interpret these SU3s as coming from punctures. That's one thing that we will do. And now we start reverse engineering. So what type of hints we get from 4 dimensions? So one I already said. is that the fact that the SU3 symmetries that we see come from punctures. Okay. Hint number 2, that there are no other, like on generic points of the conformal manifold, all the other symmetries are broken. So what we are after is a theory which doesn't have any symmetry in 6D. It only has symmetries which come from the punctures. Okay? It's a guess. Okay? It's a natural guess. And we can see, how far can we go with that guess? Okay. And again, when we combine trifundamentals, we gauge these SU3s. Okay, so now we go from 4 dimensions one step farther to 5 dimensions. So what does this guess tell us about 5 dimensions? Okay, since we gauge things by glue things by gauging SU3 symmetry, that means that we are after a 6D theory which in 5D dimensions has an effective description as an SU3 gauge theory. Okay? However, because we assume that there are no other symmetries, it has to be a pure gauge theory. Because if you add matter to it, you will have some symmetry acting on the matter. Okay? So it has to be a pure gauge theory. A pure gauge theory in 5 dimensions has still a choice of Chern-Simons level. Okay? So for low levels, people argue that the theories have a UV completion as 5-dimensional SCFTs. And exactly with level 9, if you put a level, if you consider SU3 gauge theory in 5 dimensions with level 9, there are claims, conjectures, that this theory is UV completed by a 6D SCFT, which we'll discuss on the next slide. Now, you can compute the anomalies which the 4D theory has. If you have, like, this Chern-Simons level will affect the anomalies by an anomaly inflow argument. It will affect the anomalies that the 4-dimensional theory will have, like the cubic anomaly of SU3 and so on. And exactly with level 9, you can produce the anomalies, the SU3 anomalies, which these blocks have. So level 9 is good for us. Okay? It produces the right anomalies that we have. And it also produces something which lifts to 6 dimensions. So this is our prediction at 5 dimensions. An SU3 theory with level 9 Chern-Simons term. Okay? Now, what is the UV completion of this theory in 6 dimensions? And the claim is that the level 9 SU3 gauge theory in 5 dimensions lifts in 6 dimensions to a pure glue SU3 theory. So you just take SU3 gauge theory with a tensor multiplet which is there to cancel anomalies, and you think of it as a effective theory on the tensor branch of some SCFT. And if you go to the origin of the tensor of this tensor branch, you get some strongly coupled SCFT. If you reduce it on a circle, you get the theory in 5 dimensions that we have considered. Okay. There are very few pure glue theories that can actually be consistent because of anomalies considerations, and they were classified by Seiberg and by Bershadsky and Waffa long time ago. Basically, you can have SU3, SO8, F4, E6, E7, and E8, and nothing else. All the rest, you need something to cancel anomalies, and you need matter to cancel anomalies. So these are the only candidates. And these theories don't have any continuous global symmetries. Okay, they are pure glue.
Sorry. The anomaly cancellation analyzed on the tensor branch.
Yes, that's right.
What sort of, what is the Lagrange look like?
Just pure SU3 gauge theory.
But what is the contribution of the tensors?
Okay, that we'll discuss later on. But it's you need it just to cancel the anomalies. Okay. Depending on how much detail you will want, I can go it in later lectures.
Even at an elementary level, I'm getting now. So you're talking about 6 dimensions.
6 dimensions. Yes.
Okay. So the gauge coupling is IR free.
Yes.
And the UV looks like it goes
Yes.
to infinity.
Right.
And it's this infinitely coupled theory, that strongly coupled theory that you're talking about.
Yeah, so there is some CFT in 6 dimensions. We don't know what it is. It has some tensor branch, which is analogous to Coulomb branch in lower dimensions. And when we go on this Coulomb branch or tensor branch, there is an effective description as an SU3 pure gauge theory, pure glue gauge theory, no matter. Okay. And the point is that if you look on kind of pure gauge theories in 6 dimension and ask which of them can be a description on a tensor branch of some SCFT, there is a very limited number of choices because you need this theory to be anomaly free.
And this tensor branch, what dimension is it?
One dimensional.
One complex dimension.
Yes, you add one tensor.
Okay. So there's a scale in this wave, and as you take that scale to 0, the gauge coupling becomes.
Yeah, you go to the origin of the tensor branch.
So roughly speaking, the gauge coupling is going to infinity at the end.
That's right. Yes. Right. No, I think complex, but let me get back to you with it. But I think complex. Okay.
Also, sorry.
Yes.
So when you have this theory now, when you reduce it to 5D, the level of the Chern-Simons is.
Okay. So good point. Good question. The SU3 that you have in 6 dimensions and SU3 that you have in 5 dimensions are unrelated. You have some CFT in the 6 dimensions, and you reduce it to 5D. You don't reduce the theory on the tensor branch. You reduce the CFT. Okay, and we will see later on example where the CFT in 6D has one group and the theory in 5D has another group. They are not related. And moreover, it's not just a reduction of the 6D theory on a circle. It's a reduction with a Z2 twist. This theory in 6 dimensions has a Z2 discrete symmetry, which is just complex conjugation. And you need to twist with that Z2 to get the 5D description. If you just reduce without a twist, it is not known what the 5D description is. Okay? It's not known what it is. It might be a strongly coupled theory in 5 dimensions which doesn't have a gauge theory description. So this twist is important. So again, this is an accident here that the 6D and 5D gauge groups are SU3.
I'm really sorry to keep
Yes.
slowing you down.
No,
But,
that's fine.
the gauge multiplet, 1,0 gauge multiplet in 6 dimensions. The tensor
Yes.
is part of that multiplet.
Yes.
Okay, and can you review what that multiplet is? That's got the gauge goes on, and what do you mean by this tensor? What is this? It's scalar.
It is a scalar multi. I will review. I plan to review it in the following talks. But so it's okay. So this is the statement that the 6-dimensional theory is SU3, pure SU3 glue theory. We need, when we go to 5 dimensions, we twist by this complex conjugation Z2 symmetry, and we get this 5D theory that we discussed with that particular level. Okay, there is no derivation of this statement. It's a conjecture.
So it's a conjecture that you will get the SU3 at level 9.
Yes. That's right. So if you take this 6D SCFT, which on tensor branch is described by SU3, you put it on a circle with this twist, the conjecture is that you get an SU3 with level 9 in 5 dimensions. It's rather recent. It's like the check that you can perform is to match the dimensions of different branches. These are very weak checks. And if you wish, what I'm going to tell you is another check of this conjecture, because we will produce a consistent picture. It's rather, okay, let me give you an argument. Why is it so? So people did the opposite thing. They started from SU3 in 5 dimensions and cranked up the levels. For low levels, they found some brain constructions or some constructions, some 5-dimensional constructions, which indicate that there should be a UV completion in 5 dimensions. For level 9, there is no 5D construction. So there is a conjecture that, you know, at this boundary, you should, boundary I mean by increasing the levels, there might be a 6D description. Now, what can it be? It should be a theory which has no global symmetries, because this theory in 5 dimensions doesn't have global symmetries. So this list of pure gauge theories in 6 dimensions are candidates. And by matching some simple like dimensions of certain branches, this is the only known candidate. So that's basically where the conjecture comes from. And again, the procedure that we will do now is another evidence that this conjecture is correct. Okay. So now we have arrived at a 6D possible 6D origin of our 3D model. So we will now run the algorithm the way it was supposed to be run
So I'm really
by
sorry.
nature. Yes.
You know,
Yes.
Sorry. Yeah, suppose I take this 5D Chern-Simons theory
Yes.
and 5D Yang-Mills coupling.
Yes.
And then I go to the UV.
Oh, good. So the 5D Yang-Mills coupling is related to the radius of the circle on which you compactify. Okay. For example, you should say to me that actually there is a symmetry. The 5D theory has a symmetry. This is this instanton symmetry, which for which, if you wish, the chemical potential is the gauge coupling. But it is related to the KK modes. So different limits correspond to doing different things with this circle.
Yeah, but I was going to ask a very nice question, which
Yes.
was that if I go deep to the UV, it looks like the gauge coupling is flowing to infinity. So 1 over G squared is going to 0.
Yes.
So it looks like the theory is governed purely by the Chern-Simons term. Firstly, is that naive reasoning right? And secondly, is there some sense in which it's true that the UV theory is governed purely by the Chern-Simons? I mean, we've got 1 over G squared Yang-Mills.
Yes.
G squared Yang-Mills is going to infinity in the UV. So it looks like the Yang-Mills term is dropping out, naively. Okay? K remains fixed. So naively it looks like the theory is governed purely by the Chern-Simons term in the deep UV. Is this naive reason right? And is there a sense in which one can make this precise?
Naively, I would say you are right, but I'm not sure about
Okay.
it. Yes. Okay. Okay, so before going, so now we will run the algorithm from 6 dimensions down to 4 dimensions, but before doing that, let me slightly generalize the procedure, like the discussion to other cases. So I said that there are other cases of pure gauge theories which make sense in 6 dimensions, and here is the complete list. So we can, all of them are known. For all of them are anomaly free. For all of them we can cancel anomalies. And for example, anomaly polynomials are known for all of them. Okay, the only symmetry these theories have are the R symmetry. So we can compute anomaly polynomials, and we can integrate these anomaly polynomials on the Riemann surface to produce predictions for anomalies in 4 dimensions. So when doing so, you get these types of anomalies for A and C, for example. So if you take these theories on a genus G Riemann surface with no punctures, these are the anomalies you should get. And the numbers here, lambda G and dg, they depend on which gauge theory you took. Okay? So this is a straightforward procedure, and you get a prediction of what type of theory you should get in 4 dimensions, what types of anomalies it can have.
What was lambda G?
Lambda G is this. It's some group theoretical factor which enters. It basically tells you how trace f to the 4 is related to trace f squared squared. This in a joint representation. So there is some group theory enters in this computation, and you get these numbers. Okay. So this is a rather straightforward computation to perform, and this is what you get. These are the anomalies that you get in 4 dimensions. Okay. So for all these cases, you have predictions of anomalies. But however, only for subset, very small subset of these theories, we know what the 5D description is in terms of gauge theory. This is the SU3 and SO8, which we will soon discuss. For others, we don't know what the 5D description is. So only for these 2 cases, we can add punctures to the story. Okay? So, and again, we add punctures by analyzing the 5-dimensional contributions. And to Abhijit's question from before, how we compute the anomalies in presence of the punctures. So there are 2 contributions. One is geometric contribution. It's just you integrate over a Riemann surface which has holes. Okay? Another is from anomaly inflow types of arguments. You have degrees of freedom on these boundaries. We need to add them. And I will review it in more detail in my other talks. Okay? So there are 2 pieces that we should consider, and they both contribute to the anomalies, and we need to know this gauge theory description to be able to do so. In the SU3 case, we have a conjecture, so we can produce the anomalies.
So these punctures are just manifolds with boundaries.
That's right. And but because you have boundaries, you also need to specify boundary conditions. So it's not just.
Modes living on the boundary.
So when you think of it in 5 dimensions, so there are some field. There is when you think of a 4D theory living kind of on this boundary, you have some contribution to anomalies of these 5D degrees of freedom of the four-dimensional theory. That the four-dimensional theory. It's exactly anomaly.
The four-dimensional theory is the Neumann boundary.
Yes, we'll discuss it in great detail. Okay. Okay, so now we have a prediction of anomalies of four-dimensional theory, and we have these building blocks which we conjecture our four-dimensional theories should be built from. So now we can ask what kind of combinations of these four-dimensional theories will produce such anomalies. Okay? So, for example, we can ask what is a four-punctured sphere? A sphere with four punctures with four factors of SU3 symmetries. Can we build something from such blocks which will produce the right anomalies? Okay? And here is the theory you can consider. You take actually three such blocks, gauge two SU3 symmetries, and you turn on these wiggly blue lines correspond to turning on generic baryonic superpotential. So these are like quarks in fundamental. So we just turn on the generic baryonic superpotential for these fields and no superpotential here. Okay? So we have four SU3s, three SU3s that are explicitly written down, and another SU3 which rotates this triplet of bifundamentals, and another which rotates this triplet of bifundamentals. So there are four SU3 symmetries, and they produce exactly the right anomalies. Okay? So it's not obvious that there would exist such a theory that would match these anomalies, but there exists, and here it is.
And this is with two SU3 gauge nodes, huh?
Two SU3 gauge nodes, and it's four-punctured sphere.
So one piece, three-punctured sphere.
Okay, three-punctured sphere, you are jumping ahead a little bit. Okay, not far, like just two slides. Okay, so this is our basic building blocks. This is our trifundamental. So we will have two types of blocks. One is just this trifundamental. Another is a trifundamental, but with a baryonic superpotential, which breaks one of the SU3s, just a superpotential. And then from these blocks, we can build any theory. So we can write a four-punctured sphere on the previous slide in this way. So it's one trifundamental with a baryonic superpotential, and another trifundamental. And then using these four-punctured spheres, we can build any closed Riemann surface, okay? And all the anomalies match. And we can build any surface with even number of punctures with the four-punctured spheres, okay, by gluing them together. Okay? So we can build this large class of theories.
All the propagators here are wiggly, these blue lines?
No. Only when they are wiggly, they are wiggly.
No, I mean, you cannot see this.
Oh, so here it's just this is wiggly. Yes, just this is wiggly.
Yeah, so just
This and
the
this.
intervals, all of them are that, right?
Right, so it's just think this theory is combined by taking two four-punctured spheres and gluing them together. You can combine such a surface. And the four-punctured sphere has a wiggly line.
Gluing always means gauging?
Gauging SU3 symmetries. Okay. So this is some quiver gauge theory with many gauge groups. Many gauge groups. And the statement is that this is the 4D theory that you would obtain if you will compactify the 6D SCFT on a genus 3 Riemann surface.
This is exactly like Guyotto's story.
Exactly like Guyotto's story, but it's instead of trifundamentals of SU2, you have trifundamentals of SU3, and it is important that the three-punctured sphere, and we'll come back to it, is not this building block. The four-punctured sphere is this block, or rather in more...
Gluing doesn't seem like the gluing doesn't seem like just gauging, right?
It's just gauging.
Is this
No. You should think of this as four-punctured sphere. This is your building block, and from it you build things just by gauging. Okay? I will get to three-punctured sphere in a moment.
Oh, can you go back to this?
Yes.
So that is the four-punctured sphere is the block, the main building block you're saying?
Yes, and just so here you take one such block, you add a loop, then you take another block, and you just. So the basic picture here, like you have two such things.
Oh, I see. Okay.
Two such things. So you close this one, and this one, and you produce a genus 3 surface.
So I think these new gaugings are different from the old gauging somehow.
What do you mean?
The old gauging meaning, the thing that you glued together to make the 4 puncture sphere.
No,
That was also in some sense
no, 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 no.
Yeah, the one with the blue.
So excellent question. Just wait one slide. So we have this thing, but okay, maybe better. I defined to you a 4 puncture sphere like that. That's how you should think about it, not as a combination of 3 puncture sphere.
Okay. Then crossing symmetry.
For a 4 puncture sphere, excellent question. There is. You can check it. It's not trivial. Okay, it's not trivial because in the definition, the 4, like 2 pairs come on different footing, and you need to check that there is crossing symmetry. It's not trivial. Say if you compute the index, it's not trivial.
You say that at the Lagrangian level, isn't that wiggly blue line also a gauging?
No. So this is completely Lagrangian. So the Lagrangian. So let me wipe it out. So the Lagrangian is like this. So this theory, okay, corresponds to you take 3 copies. You gauge these symmetries and you turn on superpotential, which breaks the SU3 symmetry here. So that's the Lagrangian. Okay, and this is this building block. So now, I hope it's in the next line.
So
Yes.
the first line, the theory that you had, what is how to draw this geometrically? You had as in the motivation, the beginning.
Yes, the motivation was that we need to build something from these things, and naive guess would be that these are trifundamentals. Sorry, these are 3 puncture spheres. This is wrong.
No. So you had in the SU3 theory with 9.
Yes.
Right. Which has 7
Oh,
dimensions.
yes, we will get there. We'll get there. Okay, we are not done yet. Okay, so this is the general theory that we can obtain. But now, remember that the 5D description we could obtain only if we had a Z2 twist. Okay, we took this 6D theory and we put a Z2 twist. Okay, but this means that we cannot have spheres with 3 punctures, or with any odd number of punctures, because this Z2 twist must have to multiply to 1. Okay, and if we have odd number of twists, we cannot do it. So we don't have a 3 puncture sphere, at least not with the punctures defined through these 5D boundary conditions. Okay, we might have a 3 puncture sphere, but what we mean by a puncture, like a 3rd puncture, 2 punctures might be the types of punctures that we discussed, but the 3rd puncture should be this untwisted puncture, and we don't know what it is. Okay, so that's the reason why we don't have a 3 puncture sphere. The basic building block is a 4 puncture sphere. Okay. And now, again, this is another implication of this. Now you can say, but wait, the 4 puncture sphere has a conformal manifold, one direction of which you should identify with the complex structure modulus of the 4 puncture sphere. So what happens if you take that coupling to be small or big or whatever, to go to some limit? So here is the picture of the statement. The statement is that the theory has a conformal manifold, and the line which corresponds to this complex structure modulus doesn't go through the 3 point. Okay, the full conformal manifold of this theory goes through 3 point. It's a big conformal manifold. I don't remember the dimensionality, but it is rather big. And there is a 1 dimension that you should identify with complex structure modulus. It doesn't go through free coupling. So when going to this decoupling limit, you will go to some corner in strong coupled corner in this gauge theory description. So you will still get some, you don't have a description of this decoupling in terms of weakly coupled gauge theory. Okay, so there is a 3. Exactly. That's actually not. It's the other way around. This is the picture to explain why we don't see it. It's not. It's an explanation why we don't have a 3 puncture sphere. Okay.
And in this limit, it doesn't break up into 2 pieces.
It breaks up into 2 pieces, but it's like the breaking is not like usually what we get is that when there is some breaking where we describe the combined theory as 2 pieces with weakly gauging of some symmetry. And here breaking is some other, like there is no weakly gauging of, at least not of this sort. We don't know how to describe it, how to describe that limit. Some coupling is small, but then these theories might be very strongly coupled. I mean, there might be some non-trivial description of them. And there is some weakly coupled procedure that combines them, but what is that weak coupling? We don't know. It's not
in the limit that goes to infinity, is it like the square of 2 pairs?
Well, not really, because you need to project on gauge invariant state. So we don't know what it is. Like in the cases where we have a gauge theory description, it's not a square; it's a projection.
Because of the Gauss.
Yes, so it's not. Okay.
It's almost a square.
It's almost a square, and
Yeah.
you throw away some
Yeah.
stuff. Yes. Okay. Okay. So there are many checks that one can perform. Then actually, because of your excellent questions, I mentioned most of them. So one thing you can check more is duality. So this 4-puncture sphere should be invariant under exchanging the punctures. And the description doesn't manifest this symmetry. So you need to check that, and this turns out to be true. You can compute the index of these theories, the supersymmetric index, and from the index you can read off the marginal operators and the conserved currents. For example, at particular order of the index, marginal operators minus conserved currents need to appear, and if you compute the index of a generic theory, you get that there are 3G minus 3 plus S marginal operators, then there are conserved current for the SU3s for the punctures. This needs to be S and not 3. And then there are other marginal operators which are charged under puncture symmetry, which are in the 10 representation of SU3. Okay? So there are these types of checks that you can perform.
This duality that you mentioned, is it a new thing or
It's as far as I know, it's new, but we could not reduce it. We could not, but you know, I don't know. Okay. Now we are still, as Abhijit reminded us, we are still not getting this particular theory that we started with. We get a little bit more complicated theory. So to get these theories, we can do another procedure. And we can try to close punctures. Okay? Closing punctures in this story corresponds to giving vacuum expectation values to operators which are charged under puncture symmetry. So we have some we have punctures. Punctures correspond to some symmetries. We can try to break those symmetries by giving vevs. The way it works in the Gayotto story, you just give vevs, and then with some particular vev, you just remove the puncture. You can completely remove it. Okay? We have these operators in the 10-dimensional representation of SU3 that we find, which are charged, the operators which are charged under the puncture symmetry. We can try to give vevs to components of this operator. And what you find is that you can do that, but the punctures but you cannot really erase a puncture. What you can do is produce a puncture which has no symmetry. It's again related to this Z2 twist. When you close a puncture, you might get rid of the symmetry, but the twist needs to go around something. So in these classes of theories, there are punctures which carry no symmetry, but they are punctures. Okay? And this has analogs in other cases too. Okay, so now again, you can study these flows and you can check them using index and so on, and again you get a consistent picture. Another interesting fact about these punctures, we call them empty punctures, is that the maximal punctures, the punctures which correspond to SU3 symmetries, you can think of them as combined from triplets of these empty punctures. And the way it goes, if you compute the contribution to anomalies of empty punctures, they contribute 1/3 of the anomaly of full puncture, and also they contribute to the index as 1/3 of the full puncture. So the picture is that this is related to Abhijit's question in the beginning. You have this conformal manifold. On some parts of this conformal manifold, the SU3 symmetries corresponding to the punctures are preserved. But then you can have more generic, exactly marginal deformations, which break the symmetry of the punctures, and geometric picture is that you split the maximal punctures into these triplets of empty punctures. So a theory with a maximal puncture, with an SU3 puncture, sits on the same conformal manifold as a theory with 3 empty punctures. Okay? So is this geometry clear, more or less? Okay, so now what are these theories? So for example, we can start with our 4-puncture sphere and close one of the maximal punctures to this empty puncture just by giving a vev. And these are completely Lagrangian theories, so we can analyze what happens when we give a vev. And giving the vevs which close to empty puncture just gives us this particular theory. Higgs, one of the SU3s that we have, because we turn on some vev, and we are left with just one gauging with some, and 2 trifundamentals with some particular superpotential. And the theory that this corresponds to is 3 maximal punctures and 1 empty puncture. But from what I just said, the 3 maximal punctures can be split into triplets of empty punctures. So this theory, the full conformal manifold of it, is described by a sphere with 10 empty punctures. Okay? So this is the original theory we started with. This is the geometrical picture, a sphere with 10 empty punctures.
Where is 10?
So we close one, so we start with 4 maximal punctures. We close one of the maximal punctures down to empty puncture. But then each maximal puncture can be split into triplets of empty punctures. Okay. Such a description is a description of a subspace of the conformal manifold. The full conformal manifold is where we split the maximal punctures into triplets of empty punctures.
And this here I can think as this color flavor locking when you give a web.
Yes, exactly. Yes, this flavor will be identified with this color. Yes.
And then there is this plus some extra decoupled things.
Yeah. Well. No, there are just Goldstone bosons. There is no other decoupled things. Okay, just a Goldstone boson corresponding to this. Okay, so this is the picture. So the geometric picture of the theory of SU3 with 9 flavors is a sphere with 10 punctures. Sphere with 10 punctures has the number of complex structure moduli is 7. And this is the 7-dimensional conformal manifold we find. So the duality group that should act on this conformal manifold, there should be a duality group, and it is the mapping class group of a sphere with 10 punctures. How the duality group acts on the different couplings, we don't know. This one needs to work out the map between the couplings of the gauge theory and the complex structure moduli and to understand how the group acts. It's another more complicated question. But at least we know what the duality group should be.
But in principle, a straightforward question or something?
No, because you need to relate weak coupling to strong coupling, and we don't know how to do it. It's an excellent question, and I don't have an answer to it. This is really a question one should try to attack. So this is like, an answer of what it should be, but you need to work. I mean, it will be extremely interesting to work out how it acts. So how exactly, so you have this 7-dimensional conformal manifold, how exactly the duality group acts on it? Like how exactly, like which couplings map to which coupling? Like what are the weakly like if you take some weakly couple, say the origin, like when all the couplings are 0, what is the description when you do go in some direction?
Can one not say the following thing? So when you go to this particular point on this conformal manifold where the SU3 is
Yes.
there,
Yes.
right? So at that point you can, let's say, compute the index. Right?
Well, yes,
so
sure.
you have the index should have SU3.
Right.
But now there is another thing where these SU3 split into 3
Yes.
closed punctures,
Yes.
and those can rearrange and form different SU3.
Right,
In that
but
sense,
that's
the Y group should be
yeah.
way bigger than SU3.
Well.
Because the SU3.
No, because you break them. No, we can discuss it. But my naive answer is that this will not work because you never preserve. Say what you are saying would be true if you could preserve the cartans of SU3s. You just you break everything to you once and then you rearrange them in other ways. But I don't think you can do that. Like when you break the SU3 completely. You don't break it to a subgroup. Maybe you are right and something can be done. My first answer is that you completely break it. But
You've seen the, have you looked at the Y group? I mean, the symmetric group?
no, not in this case. So that's why I don't have a definitive answer. Okay.
So you're saying this, you don't know how the duality acts in couplings because the map between couplings and this geometrical picture of the theories is not known.
Yes. If we can come up, that's something that one can in principle analyze. Like say, okay, there are these couplings, the complex structure, there is some set of coordinates on the complex structure moduli. And one should see whether there is a natural map between the two. And then if there is a natural map, one can conjecture that, whatever you do on the complex structure modular, you should do on the coupling. It's not clear to me at the moment if there is a natural map. And
so this is the difference between, in Gayato's story there was a very natural, there was a clear map.
That's right. In Gayato's story, then we know what, so the building blocks, like 4 puncture spheres built from 3 puncture spheres, are some n equal to theories for which a conjecture is known how duality group acts. Like how tau goes to -1 over tau, what exactly you are doing. There is a very concrete conjecture. We don't have an analog of that part of the story, only what is the group.
But to begin with, to understand this map, you need to find the expansion points, right? I mean, the weak
Right.
weak coupling type
So
points, and the analog of that could be the points on the conformal manifold where the 3 SU3s are present.
Yes.
And there are many probably, right?
There are many, so that's exactly the problem here. There are too many things that you could choose. I'm not saying there is no answer. Okay, I just we don't know it. Okay, so how much time do I have left? So sorry, minus a half an hour. 15 minutes. Okay, so in the next several minutes, let me just generalize this to the case of SO8. So remember that we mentioned that there are several pure glue theories in 6 dimensions. So we analyzed SU3, and we had a conjecture like we started from 4 dimensions, reverse engineered, and then engineered back. But actually, there is this case of SO8 pure gauge theory in 6 dimensions. And it is special in the sense that for this theory, we also know a conjecture what the 5-dimensional theory is. And the conjecture here is that SO8 has this triality group acting on it, okay, the triality of SO8. So if you take a twist by this Z3 subgroup of the triality group, which is S3, then and compactify to 5 dimensions, then there is you get an SU4 gauge theory with level 8 Chern-Simons term as an effective 5-dimensional description. That's a conjecture. Okay, and again, without the twist, we don't know what it is, and so one can try to predict anomalies and so on of the theories that you get in 4 dimensions, following from this information, the 6D theory and the information about the punctures. So you can compute the anomalies, and you can try to guess what the 4-dimensional theories are, and you can come up with the following prescription. That now, since the gauge theory in 5 dimensions is SU4, to glue things together, you need to gauge SU4 symmetries. So these purple blocks are SU4 symmetries now. So the way to make the anomalies work is, instead of considering tri-fundamentals, is to consider pairs of bifundamentals of SU4. For example, if you get 3 pairs of bifundamentals of SU4, and you glue them together by gauging 2 SU4s, the claim is that you produce a theory which has all the properties to correspond to a 3-punctured sphere in this compactification.
Previous case you had SU3 on some parts of the conformal manifold.
Yes.
In the whole conformal manifold, it got broken into 3
Empty punctures, no symmetry at all.
How did that got figured out? Sorry, yes.
So,
How did you figure out that?
oh, it's just that the contribution to the anomalies and to the index of an empty puncture is really like 1/3 of the full puncture. So again, this is a conjecture, but that's how it works out. Okay, so another way to see that, like there are operators in the marginal operators in 10 of SU3. So you can turn them on. Okay, you can just turn these marginal operators on, and they generically break SU3. And when you look, say, on the index which you get of a theory which has where the symmetry are broken, this exactly matches the index of a theory with a triplet with empty punctures instead of 1 SU3 puncture. And the anomalies are the same. Okay? So typically, when you have 2 theories such that all the anomalies match, they are probably the same. It's not, there is no proof of it. I'm sure you can come up with counterexamples, but it's a strong sign that these two theories reside on the same conformal manifold at least. Okay. So this is the evidence we have. Okay. So the claim is that this particular theory corresponds to three-punctured sphere. Now, what are the symmetries of this theory? So we have an SU4 here, an SU4 here. Then we have an SU2 rotating these guys, and SU2 rotating these guys. So we have an SU4 times SU4 times 2 factors of SU2. And the claim is that somewhere on the conformal manifold of this theory, the two SU2s enhance to SU4. Okay? And at that point on the conformal manifold, the description, the theory corresponds to compactification of this theory. Anomalies match, and the index makes sense. But this theory is, unlike the previous example where everything was completely Lagrangian, here this is completely Lagrangian. But if now you want to combine more general theories, like genus 2 theories or whatever, by using these blocks, you would need to gauge the symmetry which only appears at some cusp of the conformal manifold, where the two SU2s enhance to SU4. Okay? So in that sense, it's not completely Lagrangian. Okay? You have kind of a Lagrangian way about thinking of this construction, but you cannot do it all the way through.
But how should I understand the conformal manifold from geometric point of view? There is some splitting into empty punctures again?
Yes, here it's more complicated. Here actually there are not just empty punctures, there are SU2 punctures. The story is more complicated. You can split. Here also, at the end point, you're right, everything can split into empty punctures too.
Nice. Okay. And, but because each SU4 is the same level, then it should be...
what do you mean same level?
I mean, symmetric. Then each SU4
yes.
always it splits.
That's
so
right.
The number of punctures 3 times something.
That's right. Here also, like you need to check. You can actually split. That's one check you can perform. You can split this SU4 into SU2s and see that you can permute these SU2s. So then that works out.
Now, what is the dimension of the conformal manifold?
I don't remember. It's large. But the point, the claim is that it's that only at a point the symmetry enhances to SU4. Okay. So, okay, let me skip this slide. This is something about the index, and let me summarize. So we have obtained, what have we done here? So we have obtained a large class of 4D theories by compactifying these pure glue theories in 6 dimensions down to 4 dimensions. In the first case, the SU3 that we discussed in detail, it's a completely Lagrangian description. It's very, very simple, like the SU2 construction of Gaiotto. The second example is less simple, but it's actually very typical. Okay, when we have Lagrangian type of constructions, for example, for A2 type Gaiotto theories and other constructions, we can also come up with trinions which, with Lagrangian constructions which involve gauging of symmetries which appear only at cusps of the conformal manifold. Okay? So we have a description, but we cannot compute anything with it. We cannot compute correlation functions. We need first to go to this strongly coupled point, then gauge some symmetry, and then we use a lot of computational abilities. We can compute things which do not depend on couplings, such as anomalies and indices and so on. So we can compute things with these descriptions, but not everything. So this is the second point. And again, I stress that it was possible to reverse engineer this algorithm of going from 6D to 4D because we had no symmetry. The fact that we had no symmetry made this story very, very constrained. You can now come up with general 4D theories and ask where they come from 6D. And in general, it will be a complicated question to answer because if you have symmetry, you can break the symmetry in many different ways. You can embed it in some constructions in many different ways. We will discuss similar issues in other talks.
Sorry, I didn't quite understand this point. So you're saying that because we had no symmetry, you could identify the patterns?
Right, easily. Yeah, yes, we have no symmetry, and then we assume, conjecture, that we don't have symmetry because we did not have symmetry all the way. Okay, this is a conjecture. It could have been that we don't have symmetry because we've broken it in some way. That could have been. Okay, but this worked out in this case. If we have symmetry, then we know that we have symmetry, and then it's much harder game to play. We will see many examples of this in other talks. Okay, so there are many open questions, and I list them here. So first of all, can we understand these compactifications without twists? Can we understand the compactifications for other pure gauge theories in 6 dimensions? And I think the most interesting and kind of doable question is to understand how the duality acts on this conformal manifold. It might be not simple, but I think it is an ingredient that one really should try to get here. Okay, and I had lessons 2 and 3 before, and there was not lesson 1, so here it is. I don't know. So anyway, okay, thank you.
Questions? Have you given this talk at Caltech?
Okay, so Shlomo is here for the week, and we will talk to him throughout.